Welcome. In this session we're going to talk about the basics of locking and transactions. What we'll cover is the basic lock types, and then we'll go through a demo about how locks work and how you can track locks. Then we'll talk about the basics of transactions and nested transactions, and we'll have a short demo on how the different transaction statements work together. Let's start by looking at lock types. The purpose of locking is to synchronize access. And what do I mean by synchronizing access? Let's look at an example here. Let's say that you have a table with data about product prices. And each of the products has a different price. And you want to go through, you want to update those prices. You've decided to have a sale. And so for 5 products, you want to reduce their price by 10%. So the first item here at the top has gone from $15. It's been reduced 10% down to $13.50. The $20 item has been reduced 10% to $18, and so on. And these are the 5 products that you want to update. While you're in the process of changing prices, you don't want people to be able to query and get prices for products that are inconsistent. So if someone was interested in the price for, let's say, this product here that was $25, that'd be okay, because that wasn't a product that you were updating the price for. However, if somebody wanted to update and look at some of the other products, maybe they also wanted to make a change to the pricing, but instead of doing a price reduction of 10%, they wanted to do an additional $2 discount on both of these prices. You would want to make sure that all of your updates were completed before they started. The reason being is that if their update went with yours, 2 different things could happen. If your update happened first, is outlined here by this top element here. If their product went first, then the new price would be $15 times 0.9, which is reduced by 10%, and then subtracted out the $2, which would mean that the product price would be $11.50. If, on the other hand, their $2 discount happened before you were able to get yours, then the second situation here would happen, where the $2 was deducted first, making it $13. And then the 10% was deducted, which would make the price of the product $11.70. If your update and this competing update were not serialized so that they happened independently of each other, you could potentially have one product with the $11.50 price here, and you could have the other product with the $25.20 price. In this case, the prices wouldn't be synchronized, and it wouldn't be the end result that you wanted. So locks help to restrict access to data when actions are being taken against it. Okay. Locks are held for the duration of the transaction, and typically when you execute just a single statement that's making modifications to data, like an insert, an update, or delete, the transaction lasts as long as the statement is executing. The locks are held while it's running until all of the rows have been modified, and then the locks are released. And we'll show you in a minute how you can extend that to make a lock last longer than a transaction, to make it last over several statements. In this session, we'll talk about the transactions that allow you to make span statements. In another session, we'll talk about the isolation levels and how they change the types of locks that are held. There are a variety of different objects that can be locked, and the ones that you'll be most commonly interested in are row locks for a row in a table, or a key in the case of an index, page locks, and extent locks. An extent is a group of 8 pages that are next to each other, table locks, and database locks. So the types of locks that are most common are listed here. And the ones that I want to focus on first are these right here, the shared and update locks and the exclusive locks. A shared lock is a lock that's taken when data is being read. It means that I'm looking at this data. Anybody else could look at it as well. I'm not going to change it. I'm just looking. But if somebody wants to make a change, I need to finish my look before they make their change. An exclusive lock is a lock that's taken to actually make a change to the data. That's either inserting new data, updating existing data, or deleting data and removing it from the database. Whenever you make those kind of modifications, you have to have an exclusive lock on the data that's underlying. An update lock is kind of a piece between a shared and exclusive lock. It indicates that right now I'm only looking at the data, but I intend later to have an exclusive lock. So I'm going to, at some point, want to make a change, so I need to get an exclusive lock later. What this table shows is, depending on the type of lock that's already been granted, here across the top, if someone requests the type of lock that's shown here going down the side, is that lock granted or not? So in this case, you can see if there's a shared lock that's been granted on an object, let's take an example of a row. If a row has been locked as a shared lock, that means somebody's running a query against it, selecting, and their select returned that row. If someone else wants a shared lock, then that's okay. That shared lock will be granted. However, if someone wants an exclusive lock, and there's a shared lock that's already been granted, the exclusive lock is denied. And what happens in practice really is the exclusive lock waits. It says, somebody's already got a shared lock, somebody's reading through the data, so I can't get my exclusive lock yet. I'm going to wait, and my process will be blocked, is the term, until the shared lock is released. And once it's released, then I'll go ahead and get my exclusive lock. So this table shows you that you can see very quickly here that with an exclusive lock, if someone has an exclusive lock, it's incompatible with all of the other types of locks that might be granted. Once somebody has an exclusive lock on a row or a table, no other sessions can get a shared lock or an update lock or an exclusive lock. Likewise, you can see that if someone has a shared lock here, if someone has a shared lock, that they can get most of the types of locks, but of course the exclusive locks are being denied. Now let's talk just briefly here about the intent locks. So those are the other locks you see here: the intent shared, intent exclusive, and shared with intent exclusive. Intent locks are taken on parent objects. So let's take an example of a shared lock where you're doing a read against a table. It's a fairly large table. SQL Server decides at the beginning that it's just going to place a lock on the individual rows that it needs. So I can get these row locks. As it goes along, it says, okay, here's a row lock I need, here's another one that I need, and pretty soon it's got quite a large collection of row locks. Maybe hundreds, maybe thousands, maybe tens of thousands as it goes through and locks the rows that it's reading to satisfy the query. At some point, SQL Server will say, you know what, I've got quite a few row locks. Each one of these row locks is consuming a little bit of memory, a little bit of resources. I have to keep track of all of them. I think it would be much easier if I just locked the table, essentially locking all the rows in the table with just one lock, rather than having these hundreds or thousands or tens of thousands of individual locks. So SQL Server will escalate the lock. It'll say, well, I'm going to go now, instead of getting individual row locks, I'm going to try to get a shared lock on the whole table. And if the lock is granted and it's able to get that lock, it'll release all of the individual locks. It takes less resources. It's locking more than it was before. It's locking the whole table instead of individual rows. But it takes less resources to maintain just one lock than it did the hundreds, the thousands, or even the tens of thousands. So what SQL Server will do when it gets a lock on a low level object, like a row or a key in an index or a page, it will take an intent lock of the same type on the higher level objects. So if you have a shared lock on a row, SQL Server will grab an intent shared lock on the page, or excuse me, on the table. That tells the other connections, hey, you know what, I might escalate at some point. I might need a shared lock on the whole table. Haven't decided yet. I'm doing row locks right now, but I might later intend to lock the entire table. The same goes for the other intent locks. Those are locks that are taken on higher level objects that allow SQL Server to lock the higher level resource in case it needs to escalate its lock. So let's talk a little bit about lock escalation. SQL Server will take a row or a key lock and it can escalate that up to a table lock. Likewise, if it starts out locking pages at a time, and all the rows on that page, that may escalate later to a table lock as well. An interesting thing to note, though, is that SQL Server will not escalate from a row or a key lock up to a page lock. Row and key locks will go straight to table locks, and page locks will also go straight to table locks. There is no escalation path that takes you from a row or a key lock up to a page lock. Okay, let's go ahead and look at an example here. I have here a query that's querying from the DM trend locks, system dynamic management view, and sys partitions. And what this query will give us is the session ID or the connection, the type of lock or the type of resource that it's trying to lock, what type of lock it wants, and then the name of the resource. So let's take a look right now. We should only have 2 connections in our database, and right now each connection has 1 lock. So we can see that SPID number 52 and SPID number 53 both have a database shared lock on the AdventureWorks 2008 R2 database. And at this point, both of those locks have been granted. As you remember, these are locks on the same object from 2 different connections. But as you remember from the grid, a shared lock is allowed when a shared lock has already been granted. So both of these connections were able to get shared locks. Now as we look down here, you can see that the SPID that I'm currently connected to is SPID 53. So my current connection, the one that you see here that ran the query, has the shared lock you see here. This other window that's up here is the other window that we're going to be using here in the demo. That's SPID 52, and it has the shared lock as well. Okay, let's go ahead and go look at the query that's over there on SPID 52. This is a simple select query. We're doing select star, which of course isn't the best practice, but there's a reason that I have using star here. From the person table, and then we're joining against the sales order header and sales order detail. Our goal here in this query is to get a list of all of the customers and all of their sales detail. Now I wrote this as star and left out the where clause because I wanted this query to return a lot of data. My goal here is to have a query that runs long enough that we can flip back to the other tab and see what kind of locks this select has granted. So let's go ahead and do that. So I'm going to get ready here. We're going to run, and then this one. Okay. You can see there's the query still executing. Here's the locks. It just finished. Here are the locks that this query obtained while it was running. See, it has the shared database lock. And then it has some metadata schema locks on some XML collections. This is getting some XML data. And here are the intent locks that we expected to see. So here's an intent shared lock on 3 different tables: the person table, the sales order detail table, and the sales order header table. This again shows us that SQL Server is getting lower level locks, but it wants to reserve the opportunity to escalate those locks up to table locks. So here's our intent shared on the 3 tables part of our query. Then down below here you can see there's a lot of page locks. These are shared page locks against the person table, and the description that we see here is actually the file ID and page ID that SQL Server is locking. So we could actually use this information here to go out and see what data was on that page. And these locks have been granted. Let's go ahead and scroll down a little bit here. What you can see is that the majority of the locks here, in fact we're looking at, what is this? 3,816 different locks. The majority of the locks here appear to be page locks on the person table. In fact, it doesn't change until we get all the way down here at the bottom. Down here at the bottom, what we get is a page lock here on the sales order detail table. And then we have, of course, here's the shared lock for the database for the connection that I'm running the lock query in. So this query here showed us that when we ran our select query, we got page locks, most of them on the person table. Looks like our query ran against the person table first, and then for each person it went out to look up the sales order header and sales order detail. When we ran our query, we caught a lock on a page in the sales order detail. If we had ran our query at a slightly different fractional second, we probably would have gotten a lock on the sales order header table as well, and seen page locks there as well. Of course, now that the query is done, if we run this again, what we'll see is that all of those locks have since been released. All right, let's go back to our query and make a small change here. Rather than doing a select, let's do an update. What we're going to do is we're going to update the detail table because it's a bigger table. We're going to set the order quantity to be the order quantity. What this will mean is that we're updating every row now in the sales order detail table through this join. But what we're changing is the sales order quantity, and we're going to change it to be itself. So this will be an update that hits every row in the table, but has the overall impact of not really changing any data. This will allow me to have a long-running update, and then I can flip back to see the types of locks that this update is reserving without having actually any data in my database change, because I don't want to change my AdventureWorks database. I'll be using it later, and I need it to stay the same. So let's go ahead and run this, and then we'll flip back while it's running to see what locks it has. Okay. So now what we see, here my query is still executing, but it'll be done in just a second. Now what we see again for our session 52 here is the shared database lock again, and intent shared on product and sales order header. That's because we're getting intent shared here because we're going to have shared locks on the items underneath. We're not actually making any changes to the product table or the sales order header table. We also have, let's see, our shared lock on the database. Now we have an exclusive lock on sales order detail. Now in this case, we're getting an exclusive lock on the whole table. We also have an exclusive lock on the transaction history table and an intent exclusive lock on this syscall per hours. So what we have here, my colors are getting just a little bit too deep. We have the exclusive lock that we would have expected here on sales order detail, shared lock on the tables that we're reading from but not updating, intent shared, and then an exclusive lock on this transaction history. Why do you suppose we have an exclusive lock on transaction history? Well, the reason we have the exclusive lock there is that sales order detail has a trigger, and that trigger updates the transaction history table. Because of that, we need an exclusive lock on rows in both tables. And in this case, because we're updating so many rows, SQL Server decided to escalate and get a lock on the entire table rather than locking individual rows or individual pages. Now, of course, that the query is done, let's go ahead and look at this again. We can see that all the locks have been released. Now, while that update query was running, and we had that exclusive lock, what would have happened if someone else had come along and wanted to query the data? This is something that we'll look at again when we talk about isolation levels in another session. But as you can imagine, as you remember from our lock compatibility mode, we had an exclusive lock. If someone else had wanted to query, they would have asked for, sorry, this is backwards. We had an exclusive lock. If someone else had wanted to query, they would have requested a shared lock. If someone has been granted an exclusive lock and someone requests a shared lock, the shared lock is not granted. So in that case, their query would have waited until our update finished. Then they would have been granted their shared lock, and they would have been able to finish their query and get their results. Now that is modified slightly by the isolation level that's in place. And again, we'll talk about how those isolation levels interact in another session. All right. Let's talk a little bit about transactions then. The interesting story here. When I've been working with SQL Server for about 7 years, I had a coworker come up to me and ask me a question about transactions. His questions are in the form of, hey, if I have a transaction and I do this, what will happen? And I gave him the answer because it was a very simple question. But when I got back to my desk, I sat down and started to think about it, and I realized that I wasn't exactly sure. So I mocked up a quick case of the situation that he had described and found out that it didn't work the way I thought it had. So as we get into transactions, you might find that this is a little different than you imagined. It's not exactly what you would expect when you first look at it. So let's go through this and let's look at it. Let's first look at some of the basic statements. When you create a transaction, you use the begin trans statement. The begin trans statement starts a transaction, and it's finished by using either a commit tran or a rollback tran. When you do a commit tran, that indicates that the transaction is complete and all of the locks that have been granted are returned. If after you do a begin tran and do your work, you then execute a rollback tran, that indicates that all the work within the transaction should be undone and the data is restored to its previous state. And of course, again, all the locks are returned as well. When you do a commit tran, you can phrase it in many ways. You can just use the word commit, commit work, commit tran, or fully spelled out, commit transaction. And all of these are the same, and there's a similar phrasing for the rollback as well. Any of those phrasings work. When you use begin tran and then either commit or rollback tran, you are creating what's called an explicit transaction. It's explicit because you're actually defining when the transaction begins and ends explicitly. You're writing it out. An implicit transaction is one where you don't define the beginning. You can set your connection to use implicit transactions using a set parameter or a default parameter that you put into your connection. When you use implicit transactions, you don't have to write out begin tran to start a transaction. The first query that you execute begins a transaction, and that transaction is held open until you either execute a commit tran or rollback tran. As we get more into how transactions work, you'll begin to see that using implicit transactions can be helpful, but they can also be very dangerous. You need to make sure that you don't leave transactions open longer than necessary, because you can actually block other connections from getting the work done that they need to. But there is an option there to actually make implicit transactions so that there's always a transaction running when you're running a query. Now there's also a concept of distributed transactions. Distributed transactions are transactions that involve not only the SQL Server instance, but they involve other objects outside of the SQL Server instance as well. Now this might be another SQL Server. Perhaps you have a set of queries that you want to run, some on your local SQL Server instance and some on another SQL Server instance, and you want them all to either be committed together or rolled back together. A distributed transaction can bind the statements on both servers together so that they work as a single group. You also have the opportunity, if you have some kind of a third-party external source that participates in distributed transactions, maybe something that modifies the registry or an Oracle database or MySQL database or some other type of Active Directory or some other type of action, if it supports distributed transactions, you can actually have changes made to those objects bound together with a transaction on objects inside your SQL Server and have them committed or rolled back together as a group. All right, let's talk a little bit about nested transactions. Here I've colored my transactional statements in green so you can easily see where the transactions are. Here I begin a transaction at the top and I commit it at the very bottom. After I begin the transaction, I do a little piece of work and then start another transaction. I do some more work, and then I look at the tran count. @tran count is a special variable, a global variable, that you can use to tell how deep you are into a transaction. When you don't have a transaction open, the @tran count will return 0, indicating that there are no transactions. After you have done one begin transaction, if you select @tran count, it'll show 1. So where this is at in the scope of these nested transactions, this select @tran count would return 2, because at this point I am inside of 2 transactions. The main one that I started on the outside, and the second one that I started inside. So my @tran count at this point would be 2. In this example, after executing that, I begin another transaction and do some more work. But within this third transaction, I have an if statement. If something bad has happened, and you can fill in this part here with some sort of variable to determine, oh, there is some sort of error, or there's some sort of condition that indicates that this transaction should be undone. So if something bad happens, then I want to do a rollback. Otherwise, I want to do a commit. And after that, this commit here will, of course, line up with the begin transaction there, as would this rollback. They both apply to, they're both indicating part of this transaction here. However, these commands here act differently. Where the commit, you can see that I commit all the way back out. A rollback transaction rolls back all the transactions back to the outermost level. So this rollback transaction here, although it looks like it should logically be within this begin transaction, the rollback undoes all of the work, all the way back out to this begin transaction here. So a rollback in a nested transaction rolls back all the transactions back out to the outermost level. This is really important to realize, especially if you may not be in control of all of your own transactions. You may have a case where you have a begin and end, or begin and commit in your SQL batch, but within that batch you're calling a stored procedure. That stored procedure might have a begin and end tran inside of it. And inside of that stored procedure, if it executes a rollback, it will roll back the transaction that you committed, or you began on the outside. Now let's see, this commit transaction actually does something interesting as well. Let's talk about that, and then we'll further talk about how to handle this rollback situation. A commit transaction does not actually commit the work of the transaction that it's in. So even though this commit transaction here is lined up with this begin transaction there, this commit does not apply only to that begin transaction. This commit here decrements the tran count, but does not free up any of the locks. The reason for that is that there may be a rollback further out, perhaps at this point right here. And if we do a rollback here, we would want to roll back everything that's part of the larger transaction. Because of that, the commit transaction doesn't actually commit the work that's been done in between the begin and commit. It decrements tran count by 1, indicating that we have stepped out of an inner transaction. It does not free the locks up, but it waits. Once add@tran count is back to 1, the next commit transaction, which of course would be this one here, will take the tran count to 0. Then the transaction is fully committed and all the locks are released. Now the situation that I talked about before is kind of interesting, where you have a batch with a begin and end tran, and within that batch you call a stored procedure. Inside that stored procedure, it executes a rollback. That rollback will undo the transaction on the outside. What you would need to do at that point is you would need to check your add@tran count before you do the commit. So at this point right here, right before this commit, and at this point right here, right before this commit, we need to check. If this rollback happened here, this commit will fail because there is no open transaction. This rollback ended all 3 of the begin transactions. So at this point right here, what we need to do is we need to check. If our add@tran count is greater than 0, then go ahead and do the commit. If not, the transaction has already been closed and we don't need to do the commit. And that's the proper way to handle nested transactions. You always need to check as you close each one out to make sure that a rollback hasn't happened on the inside and already closed out your transaction. All right. Let's look at some additional statements. When you do a begin tran, you can specify a name and actually give the transaction a name. We'll talk about that a little later as we get back down to the bottom of this slide with the commit and rollback tran. But for right now, let's just say that the begin tran can have a name. You can use this to mark and differentiate your transactions. There's also a with mark statement. What with mark does is it places a special marker in the transaction log. And that marker allows you, when you're restoring your database, to stop at the mark where you began that transaction. Now we'll talk about that more in a session, in an administrative session where we talk about backup and restore. So we're not going to go too much in depth here. But it is important to note that you can actually set that mark so that when we talk about backup and restore, you have this background to understand that this is where it's in the begin tran that mark is set. You can also call save tran and give that save tran a name. What this does is it doesn't actually do a commit, it doesn't free up any locks, and it doesn't formalize the commitment of a begin tran. What it does is it marks a save point. It says, okay, I want you to mark a special point in this transaction here. I may want to come back to this point someday, at a future point. Commit tran allows you to pass in a name, and this name would, of course, obviously correspond with the begin tran name. but the name is really ignored by SQL Server. It doesn't do anything special. Like we saw in the previous slide, commit tran just decrements the tran count. So the purpose of having the name here is really just to provide for visual separation of which transaction this commit corresponds to help you see in your code when you're looking at it how they're paired up. Rollback tran with the name actually does do something a little bit different. It allows you to roll back to a specific point. In this case, the rollback tran name either corresponds to a specific save tran point or to the outermost begin tran. Any of the internal nested begin trans are invalid to use here as part of the name. Now I have a special note here that this rollback doesn't free escalated locks. It will free locks that aren't escalated, but locks that have been escalated are not freed up by the rollback. Let's go ahead and let's take a look at an example of these statements in use. What we have here is a script that we're going to use to look at all the different transaction statements. The first thing I'm going to do is I'm going to go ahead and create a table here. It's just going to be a small table. It's going to have one column called PK, and it's going to be an int. Now we're going to go ahead and insert the value 5 into that table. All right. What we're going to do here is we're going to do a begin tran, and then we're going to insert into the table another value, value 1, and then we'll do a rollback. So when we execute this, we can see that SQL Server tells us that there was one row affected. But when we actually go and look at the data inside the table, the row that we inserted is gone, because after we did the insert, we did a rollback. Now if we had done this query inside of our transaction before we did the rollback, we can see that the value did exist. But once we hit the rollback after that, the value did not exist. Let's run these together. The first result here, the new inserted value is there. The second result, it's gone. Now this is interesting because you may say, "No, wait a second. When we did the insert here, that's a data modification statement. So it would have needed an exclusive lock on at least the row that was being inserted in order to do that." And that is true. And if we had looked at the locks here during the insert, we would have seen that it did have an exclusive lock on that row. Well then, if that's the case, the select here would have needed a shared lock in order to do the read to see that row. And since the insert had the exclusive lock, how did the select run? Well, the answer to that is that the lock compatibility table that we saw before is intended for separate connections or different connections. Locks that you have within your own connection aren't considered when you're looking at the compatibility matrix. So because it was our connection 54 in this case here, that had the exclusive lock, we were also granted the right to actually see it. We didn't have to get a shared lock in order to read the row that we had there. There wasn't a competition for the lock. And again, now the competition between, or the compatibility between sessions for these lock types is something that we'll talk about when we get to isolation levels in the next presentation. All right. Here's a very simple transaction statement here. This one has begin tran and then it does the same insert, but in this case, instead of doing rollback, we're doing commit. So we execute that. Again, it tells us one row affected. But when we look at the table, we can see that the value is there. Because we did the commit, the locks were freed up and the data modification was allowed to remain. All right, let's look at something just a bit more complex. All right, what we're going to do here is just first let's look and let's see what our tran count is here, our transaction depth. Currently we're at 0 because we're not in a transaction. Now what we're going to do is we're going to begin transaction and we're going to give it a name. The name we're going to give this transaction is Acrame. Now if we look at our transaction depth, we can see that we are at a depth of 1. We're inside of one transaction. We're going to go ahead and insert another row, a value of 2 now. Look at our depth. Okay, so the insert did not change our transaction depth. The statements that change our transaction depth are the begin tran, rollback tran, and commit tran. Actual making data for modifications doesn't change the depth we are in a transaction. We're still at the same level. Now we're going to do a save tran. As you remember from the slide, the save tran gives us a point that we can go back to. This is different than begin tran. We're still at transaction depth 1. The save trend is a marker within the transaction that we've already started, a place that we can go back to. Save trend also didn't change our data. We still have the original value of 5 that we inserted, the value of 1 that we inserted from our previous test, and the value of 2 that we inserted as part of this level 1 transaction. Let's go ahead and do an update now. Let's change our original value of 5 to 10. Okay, we can go ahead and see that change. Now we're going to make another save point. This one we're going to call save trend 2. Now again, that save trend does not increase our transaction depth. It's just a marker within the transaction we already have open. Let's make another change here. Updating it, went from 5 to 10. Now we're going from 10 to 15. Now when we look, we can see that the value did change. Now what we're going to do is we're going to do a rollback. And the rollback that we're going to do, we're going to give it a name, and we're going to say roll back to this point here, my save trend. That's my save trend is all the way up here. So let's do our rollback. That succeeds. Now let's look and see what we have in our table. We're back to 5, 1, and 2. So these changes that we made after my save trend, which is where we updated to 10, and then from 10 to 15, have been undone because we rolled back to this point here, my save trend. Now if we wanted to now roll back to my save trend 2, which is after my save trend, it'll tell us I can't do that. Cannot roll back my save trend 2. Couldn't find it. The reason it couldn't find it is because when we rolled back to my save trend, we rolled back this marker as well. So it's gone because we rolled back past it and undid the marker existing. All right, let's go ahead and redo this. We're going to redo our save trend. We're going to redo our change from 5 to 10. We're going to redo save trend 2. And then we're going to redo our update from 10 to 15. Let's take a look here and make sure. Sure enough, 15, 1, and 2. Now let's do it in the opposite order. Let's roll back my save trend 2 first. Okay, allowed us to do that. Now if we look, we can see that we're at the state we were right when we had my save trend 2. We've updated from 5 to 10, but we undid the part here where we updated from 10 to 15. Now we can do roll back to my save trend now as well. My save trend is here. It was before my save trend 2. We've come to this point, which means that all the stuff before it is still there, including this save point. So we can roll back a little bit further. We can step back one more step. When we do that and then look at the contents of our table, we can see that we are back to the point my save trend. So we can step backwards, and just like you would expect a queue, the items that are in the queue are still there. The ones that are undone are the ones that were at the point where you executed the save trend. Okay. All right, let's scroll down here a little bit more. All right, now what we're going to do is we're going to begin a nested transaction. So we're still in our Acrame transaction, and we're going to start a new one, and we're going to call it nested. Now when we look at our transaction depth, we can see that our transaction depth is now 2. That's because we have started a second transaction. So now we're 2 deep. Now we go ahead and do our update, and we're going to update the value 5 to 20. As you remember, the value is now 5 because we rolled back all the way to save trend. So we undid the 5 to 10 and 10 to 15. So we'll do our update. Then let's go ahead and look at the contents of our table. We're at 20, 1, and 2, just like we'd expect. Now, if I want to roll back to this begin trend, I'm not allowed to do that. The reason I'm not allowed to do that is because I can only roll back to a save trend or to the outer transaction name. Any of the internal nested transaction names are not allowed in the rollback trend. That helps us to remember that really the name here for begin trend is really to help us remember where we're at, to remember where we are at in our transaction nesting. A rollback trend either goes to a save point or all the way out. So rolling back to a nested transaction point doesn't make any sense. We're going to roll back all the way, or we're only going to roll back to a save point. So at this point, we can do a rollback tran to the beginning. Let's look at our transaction depth right before we do this. We're still at transaction depth 2. So then we can provide the name of the outermost query, outermost begin tran, and that will succeed. And that takes us all the way. It doesn't take us to transaction depth of 1. It takes us all the way out to transaction depth of 0. So of course, now that we've done a rollback here, it doesn't correspond to the nested one. It corresponds to the entire query. So if we, or the entire transaction. So if we did a rollback here that should correspond with our initial begin tran for Acrame, we can see that of course it says no, I can't do that. Now I had the question here in the comments that the rollback tran Acrame succeeds. What would a commit tran? Well, if we hit commit, that would have just been a crime. If you have any questions that I haven't answered about transactions, you're welcome to come by, visit with me, and I can answer your question in person. Or you're also welcome to send me an email or shoot me a note on Twitter at DBAchat.